Hello, welcome to this event of the Maryland STEM Festival. Today I have with me Jeremy, James, and Danny from Dankmeyer. They are going to be talking to you about a very important technical medical issue, prosthetics. So I'm going to turn the program over to the gentleman. I'm going to turn it over after a couple quick comments. If you would like to post or tweet about this event while it's going on, our hashtag is MDSTEMFest. If you have any questions, please put them in the chat box and I will relay them to our presenters. And at the end of the event, I'm going to post a link to our survey and we would appreciate if you complete the survey. So after those brief house cleaning announcements, I will turn the program over to our folks from Dankmeyer. Thank you very much.
All right. So hello, everyone. Hope you guys are all doing well, staying safe out there. My name's Jeremy. This is James, and then Danny is over here. Yeah, let's get to it. So we're talking about orthotics and prosthetics. Dankmeyer is an orthotic and prosthetic company. So we service patients. We build prosthetic and orthotic devices, and that's what we're going to talk about today. Try to talk about some of the misconceptions, talk about some of the things that we do, how we do them. And then if you're interested in how you can learn more. So actually, I'm going to let Danny go ahead and talk about the education portion of it first. Danny is our resident, so he is still in the process of completing his prosthetic education and certification. I guess I should say, you're done with your education, working on the certification. So in order to become a certified prosthetist, after you go through your schooling, you have to do a residency where you practice and start to actually put what you've learned into the field and actually start treating patients. And so that's what Danny's at right now. And I'll let him talk a little bit about the educational experience, and then we'll kind of get into the rest of it.
Sure. Hi, everyone. I'm Danny Weiser. I am a resident prosthetist orthotist here at Dankmeyer. I've been here for about coming up on 3 months. I just finished my master's degree in prosthetics and orthotics at Northwestern University, which is now, within the past 5 years, has been a requirement in order to be able to sit for my certification, become a prosthetist orthotist. You need to have a master's within the field. Prior to that, it used to be just a bachelor's degree. And prior to even that, it used to just be a certificate. So you spend some time, a couple of months through a program, and you got a certificate at the end. And then it became a bachelor's degree, which most of you already know how that goes. And then it became a master's. So you would have an undergrad that could either be within engineering, like bioscience, biology, anatomy, anything within the healthcare field. And then you would go on to a master's program that would host for prosthetics and orthotics masters. There are not many of our master's programs within the country. I believe as of now there are about 13. There are 13. So that's the last count. So there's not many. It's not a very, very large field, which is both neat and sometimes frustrating because there's still a whole lot to learn and not many people to ask. So we learn based on experience. Jeremy said before that I finished my education, but I disagree with that because, within our field, it's a lifelong education. There's tons of experience to be learned and earned. And like even today, I learned something brand new within fabrication, which I did not learn in school. So it's a lifelong learning experience. If there are any questions pertaining to education or to the education components, happy to answer them. Again, I went through the program at Northwestern University out in Chicago, which is one of the larger programs. We had about 48 students. A lot of the other programs are a bit smaller, usually housing between 8 and 15 students. Because our field is so hands-on, we have both the classroom setting learning, and then we have the lab setting learning. The lab setting is where we do our fabrication, making the prostheses and orthoses, seeing the patients, casting them, and then getting them onto like practice prostheses, unorthoses. So not many schools have the capabilities of housing too many students at once. Their labs are relatively small. So we were very lucky to have a fairly large lab and have a large patient pool to work from. Yeah, it was actually really, really, really cool experience. If anyone is interested in learning more about the schooling and have any questions, you can feel free to reach out to us. We'd be more than happy to answer those.
Absolutely. Thanks,
Awesome.
Danny.
Thank you.
And also might as well mention as well, if you really are seriously interested, one of the best things you can do is reach out to local orthotic and prosthetic companies. Usually we have tons of students coming through, especially during the summer. Unfortunately, COVID has put all of that on hold right now. We would love to resume. We have plans to resume next year, but of course that's all, barring that this COVID situation is under control. But between that, and then if you want to look more information online, the National Commission for Orthotic and Prosthetic Education is your go-to place for everything. All the schools, links to the programs, actual prerequisites, things like that. So that's ncope.org. Just Google that and then I'll take you right to it. So yeah, that's the basis of the education. And all right, let's move on. So what is orthotics and prosthetics? It's prosthetics is replacing missing body parts. Most people kind of already understand what that is. If you have an amputation, we try to figure out ways to replace that, whether it's fingers, toes, legs, all the way up to hips, which is a very challenging level, including arms. And then orthotics is kind of the counterpart to that, which is bracing intact limbs and body parts. So we can do bracing from everything from the feet, hands, torso, everything in between. So that's kind of the difference between the two. They're very similar, yet very different. They have their own sets of challenges that, oh man, that's half of what school is. But yeah, that's the basics between the two. So to talk a little more about prosthetics, I thought, Art, we could start off with having you give a brief history of kind of where we have come from.
Okay.
And yeah, we'll go from there.
Step in. Yeah. Really sort of interesting looking at the history of prosthetics. They say one of the earliest prosthetics ever found was on an Egyptian mummy. There was a toe carved out of wood and using some leather as well to strap it on. They don't think it was very functional, but it was that's one of the first examples they've ever found. Prosthetics sort of, you see some of the crude prosthetics, maybe some old movies. You see the pirate with the peg leg, things of that sort, and the hook for a hand, as in you've seen Captain Hook. But prosthetics really sort of took off into a modern age during the Civil War. And one of the reasons for that is that the technology used for warfare became better. Rather than using just musket balls, they started using something shaped more like a bullet. And the guns were more accurate, so there were more injuries. So during the Civil War, they had a lot of dealings with amputations. And one particular person, his name is James Hanger, created something for himself because he really didn't like what the peg leg that they made for him, including hinges at the knee and hinges at the ankle, so it was a more natural walk. And he ended up getting a contract to make prosthetics for injured soldiers. A little more advanced advancement came with World War II. Again, there were more people in need of the products. So and then, I mean,
here we have actually some old examples.
This is a nice old example. I mean, you can see it very well, but it's, we can see if we can zoom in there, take a quick look at that. But you can see it's got straps and buckles and leather and wood and rubber became an interesting product because it was more flexible. They could start working with that. Then during World War II and beyond that, they started using some different materials such as carbon fiber, different fabrics, resins, all kinds of things to actually create the sockets.
Yep.
Again, if you want to zoom.
Gentlemen, someone asked, what does bracing mean? And someone else replies, stabilizing an intact joint. Do you want to expand upon what bracing is?
Sure.
Okay.
Yeah, so orthotics that's partially right. We are stabilizing a joint. They're not necessarily always intact, meaning normally they're not functioning properly, whether it's a muscle function or stabilizing ligaments, things like that. So yeah, that's partially correct. But we're bracing existing limbs and creating superstructure to surround them and to support them.
Yeah. So bracing also, orthotics also is not just talking about the inserts that you would have in your shoe. So we would do like scoliosis bracing to help fix scoliotic curves that are abnormal. We also do like cervical bracing for those who happen to be, say, in a car accident and has some cervical issues. We also do halo bracing, which are getting higher up on the skull to control the higher vertebrae within the skull itself. So there's a whole gamut, I would say, of bracing. So it's not just orthotics that would be inserts within the shoe. Art's got what we have. It's called an AFO, which it's funny because a lot of the names for these orthoses really come from the joints or the areas on the body that they cover. An AFO stands for an ankle foot orthosis, which we would have the ankle and the foot encapsulated, as well as part of the calf. So that's the name for this. And then we have this as a TLSO, which is a thoracolumbar sacral orthosis. It's quite a mouthful, but it encompasses those areas on the spine, the thoracic, the lumbar, and sacral portions of the spine. And again, this is for like scoliosis, or even, larger, forgive me, spinal fractures and whatnot. So I hope that answers or helps answer that question.
Okay. So talking about actually building, which is what I do, we use a lot of different materials. Now, got a couple here. Carbon fiber, as I mentioned, is a material that we use on a regular basis, and you've probably seen carbon fiber used in car manufacturing in some other areas. By itself, it's it's fabric. I mean, it's not going to support much. But with using that with a resin, it will become stiff and very, very tough. So yeah, you can see. Another material we use, which is sort of surprising, is called basalt. It's very similar in the fact that it's a fabric. It's woven, but it's made from basalt is actually a volcanic rock, and they have a way of making that into a thread and then weaving it into a fabric. Another material we use is called niglass, which is a combination of nylon and fiberglass. So again, we use a lot of the fabrics. This is for hard sockets. We also use a lot of plastics, as we do for the bracing, for the orthotics. A lot of people will just do a standard essentially flesh tone socket, but then they can also develop that further so it's more lifelike. We use a foam material, very much like your pool noodle, to create the shape, and then cover that with in this case it's the nylon to make something that's a little more realistic. but there are also people who like things to be personalized. So we have some samples here. We have one with the Maryland flag. We have this one. I don't think you can see too well, but it's covered in glitter. We have people who are sports fans. Like I say, we have the Maryland flag. This one for the Ravens. We have for the old hippies around there. We have the tie-dye, which is one I always enjoyed. But a lot of different materials. And the way these are made is they, as Jeremy said, they will cast the patient. They will wrap the patient with sometimes fiberglass material or sometimes plaster bandaging to get the exterior shape of their limb. We will then pour plaster into that shape and make something that's more like this. And they've been drawn on this just for teaching purposes.
When we teach, there's certain areas that you can, you need to relieve, in certain areas you can press on the body.
Right. So once we've poured that, then it's up to the practitioner to modify it to to areas they know. There may be a patient who has sensitivity in certain areas, so they're going to open that up a little bit, relieve that, and then we'll use that to make first the test socket, which is
there's something right over there behind you.
Clear plastic. Yeah. So something like this might be used for the patient to try out first, and when they fit that on, they can see where it's pushing too hard or where it's open, and they can make notes as to how they're going to modify it even further. Once they've decided everything fits well for the patient, then we'll make the final socket. As this one happens to be a carbon fiber look to it, but we will take that plaster mold that they've modified again, and we'll actually cover it with the fabrics and introduce a resin into that, and it's done under vacuum. So you would put this on, we put the fiberglass, whatever combination it's going to be, and then cover that with a material called PVA, which is a waterproof but flexible material, and then put the resin in there under vacuum, and that pulls the whole thing down against the form. And after about 20-30 minutes, it hardens and is ready for shaping. So then we then take it and shape it down to the final trim size and add the other componentry. A lot of people recently have decided they're not worried about the realistic looking leg. They just, they're just going to show it off. Sometimes they refer to it as showing their metal.
Yeah.
So.
All right. Yeah. Thank you, Art, for the brief, quick overview of fabrication. There's quite a bit to it, a lot of steps, and that's a big part of the training is learning and knowing how to fabricate, knowing what the limits are. But yeah, that's a general overview of how most things are made. The same is true for bracing as well. We're making the different custom orthoses. We are also using plaster models in that case. Part of what I'm doing is trying to work at moving more of that digital. So we do have 3D scanning technology and software to do modifications digitally rather than with a plaster model. You're using a three-dimensional model. And then that gets sent to a robot carving machine that carves it out of foam, and then we kind of use a similar process from there on. So we're still taking a shape of the body, turning it into a shape that we can modify and change, and then producing a shape that we fabricate something over top. And that's the general process. So yeah, we touched on kind of carbon fiber and what it is. And the next thing we want to talk about is the talk that everyone, all the news outlets cover and all is robotics and prosthetics. What does that actually mean? What is it? What is actually going on? People talk about brain control things, and That's not really accurate. Sort of. It's sort of accurate, but really when it comes down to it, that's not what we're doing. There are a few research cases out there that are working at directly interfacing with the nervous system to create the motion desired, but that's not really what's occurring. That's not something that's available to fit to patients. It's not gone through the proper testing. So there is actually a company here in Baltimore that has done a bit of work in what's called pattern recognition, which is the next level of control strategy for upper limb amputees. And they've actually loaned us a system here to try to see if we can demonstrate that today. So what's actually occurring when someone is using a robotic or myoelectric controlled prosthesis is they are using different motions and firing the muscles that are left in the residual limb. When they do an amputation, they take the muscles that are still there and reattach them to the bone. So they're still there, they still function. Nothing's changed. They're still wired the same way in the nervous system, unless there's an injury to the nervous system. And so they still work. So when someone thinks about closing their hand and the brain tells the hand to close, those muscles still fire in the same way that they would if your hand was there. They just don't connect to anything, so they don't really do anything. But we can take advantage of that. And up until recently, the best pattern of control was to separate it out into a couple of big motions. You can type and talk at the same time. So we would be able to put electrodes on the skin that sense and pick up when the muscle fires. So when your muscles fire, they generate a small electrical charge, and we have ways of reading those by placing something on the skin and getting contact with the skin. So up until, just a few years ago, basically when we would train amputees, we would say, think of opening. Open was moving your hand like this, and closing was doing this. So you were training people to do a different motion than what that you actually do to perform the action. So there's kind of a learning curve with that, and it takes a while to get used to that. And this only allows for one action at a time, and you can only open and close. So as hands started advancing, you get into multi-articulated hands where you actually have motors that drive each individual finger. That became a limitation. So rather than separating everything out into two movements, there's several different people that kind of started a couple different companies at the same time. So there's a couple of these out here. We just happen to have one in Baltimore. But pattern recognition is where you place, rather than two electrodes, you place an array of electrodes all over the socket. The pattern of placement is actually random. There's not a set pattern. As long as you're covering the muscles that are there and able to pick up and read from them, you can use that to your advantage. So then pattern recognition, rather than reading big motions, it can still do that, and it's very reliable. But we can tell people and train people now, okay, practice, think about closing your hand, and then the prosthesis will read the signals that are from the muscles when they fire, and interpret that and assign it to a grip. Hopefully this works well. I was having a little bit of trouble with it yesterday, but we're gonna try this out and see if we can get it to work today. So we want to make sure we have good contact with the electrodes and skin. So I'm just putting a little rubbing alcohol on my arm. My last calibration working. It might actually work. Normally when you put these on, you have to train the prosthesis what each of the motions are. Let's see if I can zoom in here a little bit. socket's right behind it. It's going to make it hard to see. There we go. There we go. I think you can see that. So, right, if I make this grip, the prosthesis will make a similar grip. There's my hand. So if I open, the hand will open. Man, I am getting all kinds of lucky today. This never works the same way. Usually you have to train the prosthesis. Every time you put the electrodes on, they're in a slightly different position. So usually we have to train the prosthesis what position, when the muscles fire, what that position means. So, you know, we can even have it mimic hand motions. I don't know if you can see that there. There we go, right? You make a, like the OK symbol for pinching, right? That's a useful grip, or grasping general objects. And then this one actually has the ability, if you move your thumb to a different position. I was having trouble with this grip earlier. Now this one's not working as well because I haven't calibrated. But I did want to show you guys what the actual muscle readings look like whenever we're now it's going to start misbehaving. All right, so hopefully you guys can see the computer screen there. Do you guys see that very well?
Okay, you can see it a bit. It's not super clear.
Okay, you can bring it closer. Yeah, just straighten in a little bit. And I can shoot this down a little bit too. There we go. So what you're looking at is there's lines, each represent an electrode that is on my skin. So then as I make different gestures with my hand, you'll see different spikes. And so what we're doing is we're taking the software and we go through a training procedure, both with the patient and with the device itself. And we teach the patient to make a repeatable signal. So part of the beauty of this whole system is I don't care what muscles are actually firing, as long as a patient can associate this pattern of muscles or this grip thought with a repeatable signal, we can train the software to recognize that as a specific signal that performs an action to the hand. So what you're looking at here is just the waveform of my muscles firing, and I'm just moving my hand in a couple different positions here. So you can see the different colors behave differently depending on which muscle they're closest to when it's fired. So hopefully that answers some questions regarding what is actually possible with myoelectrics and where we actually stand in regards to what patients can actually have access to. Zoom out. There we go. See if we can zoom out here. Thank you, Danny. All right. So normally I would ask if there's any questions. I guess we can't do that. Yeah, so that's kind of where we're at with myoelectrics and pattern recognition. So there's definitely YouTube videos out there of people using these devices. Some of them put out by the manufacturers. So yeah, feel free to go look that up. It's really interesting, and it's kind of the top of the accessible technology that we have in the field currently. So let's see.
You talked about 3D printing or?
Oh, that's right. Yeah, we also are doing some 3D printing along with the scanning. I actually have a 3D printed check socket here. That's not quite as useful in the way you'd think it might be. I'm sure you guys have all seen these open source projects that talk about being able to just 3D print something. It's definitely a lot more complicated than that. Everything that we do is designed to the individual patient, whereas a lot of the open source things are just kind of general. Yes, they can be customized. Yes, they're useful, and yes, they're fun to do, but it's not quite as plug and play as sometimes that people make it seem.
Yeah.
We also use 3D printing to kind of make different tools around the shop, make different parts when we are building prostheses. Oh man, I should have brought that one from Sean when we were fitting the that arm.
Oh, right.
We had to make a custom housing to house components for a test prosthesis. And one of our technicians designed a system kind of from the ground up and printed it so we could house all of our electronic components. So yeah, 3D printing, while you can make prostheses with them, it's certainly limited. It's got a long ways to go before it's readily available and strong enough.
Mm-hmm.
You have layer adhesion issues. Anything else, Art?
Okay.
So I was going to talk a little bit more about the educational component. As I mentioned before, one of the best things you can do is go observe someone in the field. That's how I got started. There was a family friend that was in the field, and I didn't know what I wanted to do in high school. I kind of blended my interests, so I went and I checked it out and thought it was pretty cool. So I was sold on it ever since then. So hopefully things can get cleared up with COVID and we can start doing that again. We even had one of our own come and did an internship at Infinite Biomedical Technologies, which is the company that developed this pattern recognition system. So one of our practitioners interned with them for a while. So it doesn't even have to be a direct orthotic and prosthetic. As far as schooling, if you're interested in this, focus on anatomy and physiology. You have to know bones and landmarks and origins and insertions of muscles, and all the parts of the bone, all the parts of the individual bones. And it gets, there's a lot of memorization, a lot. So start working on that early. Anatomy and physiology are good. Physics, of course, math, chemistry. We use all of these things on a daily basis. And then, yeah, prosthetics. Art, how did you get into the field, Art? I don't know if you want to talk about that. You're a technician, which is a little bit different from a technician.
I got into it sort of through the back door. I originally was a graphic artist. I did that for nearly 40 years. And the last place I was working designed phone books. And some of you are going, what's a phone book? The internet sort of took that whole process, that whole industry away. So I was left sort of high and dry. And my son had been working here. He took an internship when he was in high school and came on as a technician. He's been doing it for 22 years. And he said, you know what? They're willing to train people to do the prosthetic construction. And I've done all kinds of hobby work. I work with wood, and I work with plastics and all kinds of things on more of an artistic vein, but that came in handy. At one time when I was younger, I thought I'd like to do sculpture. Well, when I take a chunk of foam and got to carve it down and make it look like a leg, that's what sculpture's about. So I didn't think I'd have to use that skill again, but it came in very handy.
Yeah, this is a very diverse field. You have to have a lot of different skills that sometimes don't seem to relate. So very technical and yet very artistic.
Yeah.
Getting into it, I probably learned that a little bit the hard way. Getting into it, I try to make it into a simple science, and it's just, unfortunately, it's just not that way. every human is different, and the human body changes on a consistent basis. And that's part of what our job is to keep up with those changes and make changes to the devices as their body changes. So.
And I'll tell you from my standpoint, it's a very rewarding field.
Absolutely.
To work with, to know that you're helping somebody get back on their feet, to give them back, some independence where they may have been dependent on someone else to get them around, simple things,
Yeah.
Being able to feed themselves, being able to like I say, get up, get around.
Yeah, things we take for granted, standing up to go to the bathroom. If you don't have a leg, that's kind of hard to do. So yeah, being able to walk around your house and get in and out of tight spaces, in and out of vehicles, that's all things we take into consideration when we're building devices for patients. So part of that is, also developing the relationship and really learning to understand what the challenges of that unique individual are. No two people are alike. You'll never do the same thing twice. You may build many of the same type of device, but it's never the same. So it always keeps you on your toes, and that kind of echoes what Danny was saying earlier. It's an ever-changing field. Always trying to stay up on the latest technology and new ways and new methods, and even on the individual level with your patients. Your patients are changing all the time, so we have to keep up with that. Have to make changes, of course.
Yeah, I mean, we have cases that come in and somebody says, well, here's what they had before, but this has changed now, and you got to come up with a way to make that work. Sometimes we even just in producing a socket, there are things we have to sort of brainstorm. And how are we going to get to that point? As he said, there's this arm that he and my son were working on. They had to figure out, there's all these pieces, there's batteries and electrodes and all this stuff, and you got to figure out how to put that all together and make something that still looks pretty decent.
That's certainly a challenge. Yeah.
So that's always fun.
Yeah, and working, part of that is, working as a team on the back end as the clinician. We're typically interfacing directly with the patient, talking with the patient, and then the technicians are the ones that are doing a lot of the hard work of the construction. And we're kind of helping put our heads together. They're the experts in the building, and what we can and can't do, and what's safe and what's not safe, and what will tolerate the loads properly. And then we're kind of directing, well, what is the outcome? What is the need? What are the needs? How do we need to, support this body segment? It's a challenge, and it's a fun one. It's a fun one. So hopefully this gets a couple of you guys interested in prosthetics. Don't hesitate to reach out. We'd love to talk with you. Unfortunately, like I said earlier, we're not doing any interns at this time, but if you're interested, I'm more than happy to talk with you. We can definitely get email out there.
Gentlemen, do you want to give me one of your emails, or should I hold it?
Yeah, I can do that.
Okay, I'll put it in the chat box.
Okay. jhalteman@dankmeyer.com.
Please spell that. J.
Yeah, that's fair enough. J.
Someone asked when COVID is over, can high school students intern?
Yes, we frequently have high school interns. There is a application process that is outlined on the website. So yes, we frequently have high school students every year. Yeah.
And the website is
dankmeyer.com.
Okay. dankmeyer.com. And I'm sorry, spell your email again.
JHALTEMAN.
At Dankmeyer.
Yeah.
So I've put both their website and Jeremy's.
Yeah, that's right.
Okay. Email address. So if there are no further questions, I'd like to thank Jeremy and Danny and James for this excellent presentation. I hope it has inspired you. My son did an internship there at Dankmeyer, and he's very interested in going into medical devices and very much enjoyed his internship there. So thank you, everybody, for joining us. Thank you, gentlemen, for presenting. Again, this will be on Facebook, indefinitely, and we will be posting it later on our YouTube channel so you can watch it again, and also encourage others who might be interested in this. So thank you, everybody. Have a great weekend, and please fill out the survey and attend as many. Actually, on Tuesday at 4 p.m., we have another program, a biotech expo, where we have 3 or 4 different companies talking about different areas in biotech. One, we talk about proteins. One, we talking about printing lungs. So if you're interested in biotech, please check that out. So thank you again, everybody. Have a great weekend, and keep stemming.
Absolutely. Keep working hard.
Yes. All right.